Let me circle it. Circling would probably be better. I'm taking all of this and plugging it in for x to the 10th. And let me just put that down below. So putting that in, we are going to end up with 12, choose 10 to the a squared times 10, choose 6, b to the 4th, c to the 6th. Well, rearranging this, we would just have 12, choose 10 times 10, choose 6 times a squared, b to the 4th, c to the 6th. Now all we have to do is take our calculator out and do 12, choose 10, and multiply that by 10, choose 6, which comes out to 13,860 if you go ahead and plug that in. Kind of an involved problem. You have to realize that we have to put it in binomials. So this probably wouldn't be on the test. The way I'd put it on a test is as a bonus question, one worth extra credit points. Okay, any questions on the steps? I know they're kind of involved. Does it at least make sense for the one time I went through it? Okay. All right, and then you also said 71? So 71 was, what is the leading coefficient? Am I good to clear this? Okay. It says, what is the leading coefficient if we have a to the 5th, b to the 8th? And it says that this is coming from the expansion of b. I'm going to change it to plus negative 2a to the 13th. There's a few ways to do this. The way I like to do it is I just look at, well, in order for me to have a to the 5th, I must somewhere in there have negative 2a to the 5th. So I'm going to go ahead and plug that in. So we're going to have negative 2a to the 5th, b to the 8th. Because at some point, in order to me to have a to the 5th, I must have had that negative 2a in there as well. Now, to get the leading coefficient of that, I'm just going to use my choose function, or my combination, which would be 13, choose, and I'm just going to pull this 8 out of here. Kind of a fun side fact. If I would do 13, choose 5, or 13, choose 8, I'm going to get the same thing out. I'll get the same information out. All right. Now it's just a matter of pulling out that 2. So we're going to have 13, choose 8, times negative 2 to the 5th. And I would have a to the 5th, b to the 8th. Yep, that all works out. The reason why I didn't have to change the b is because b was already... If this would have been 2b, I would have had to put 2b here. I would have had to put 2b there to get that out. Yeah, that's all right. All right, other questions? Go once, twice. Okay. Today we are talking about probability. I should go back to the original slide. We're going to talk about probability, and we're going to start out with simple probability. Then we'll get to compound probability. We'll get to some new stuff tomorrow. Simple probability is, as it's stated, it's probably the simpler of the probabilities. It just consists of one event. Just one thing happens. It is calculated by dividing the number of outcomes over the number of possible outcomes. It can be displayed as a fraction, a decimal, or a percent. More often than not, we are going to use just the fraction. You will know to use percent because I will specifically say, give me your answer in percent. Or the problem might already be in percents. I might say the probability is 40%, this probability is 60%, what's your total probability? Then you know to give me the answer in percentages. But otherwise, we're just going to stick with fractions. So our first one, we have Bobby rolling one die. He's rolling a 6-sided die. From here forth, if I say just a die, it's to be assumed it's 6-sided unless I specifically say we have like a 12-sided die or something. But it is to be assumed to be 6-sided unless I specify otherwise. So he's rolling a 6-sided die. What is the probability P? He will roll a 2, which the symbol for that would just be P, probability of 2. So just P2. It can cut down on writing down stuff. All right. The first thing I want to look at is what are all his possible outcomes? Sometimes when it's something as small as dice or flipping a few coins, it's nice to draw your problem space, which is just all your possible solutions. So if he's just rolling a die, he could roll a 1. He could roll a 2. He could roll a 3. I know, it's exciting stuff. Could write a 4. He could write, oof, that's a weird square. He could do a 5. Oh, you know what I could have been doing this whole time? Look at that. That's a much better square. He could do a 6. Those are all his possible outcomes when you roll a die. So that means on the bottom, he has a total of 6 potential outcomes or possible outcomes. He wants to roll a 2, so we just have to look at how many times out of that 6, 2 is possible. Well, 2 is possible only once. There's only one outcome that results in a 2, and that is him rolling a 2. So that's going to be 1 outcome versus 6 possible outcomes. So our probability is going to be 1 over 6, and we're just going to leave it as a fraction. If I asked for a percent, you would just plug in your calculator and you'd come out with something like 16.7%, I believe. As if I asked for a percent. All right, the next one says, find the probability of observing a number larger than 4 when rolling a single die. Once again, we are rolling a single die. So the bottom of my fraction needs to be a 6, because those are still my possible outcomes. Those are my possible outcomes. From here on forth, I would probably just put possible. Outcomes is a cumbersome word to write all the time. All right, now I'm just looking for how many, if I roll a die, how many possibilities are there that it's actually bigger than 4? 2, and what are they? 5 and 6. So there's 2 possibilities. I could roll a 5. Maybe I'll write that. I could roll a 5. Or I could roll a 6. So our probability is 2 over 6, but we're always going to simplify down to 1 over 3. Our answer is 1 over 3. Our next one is finding the probability of observing a sum of 5 when a earthquake happens. No one else saw that? Did I just seizure or something? Okay. Okay. Whew. Very localized. Yep. All right. We're looking for where is there a sum of 5. Now, I went to the trouble of typing all... I didn't type them. I just found a picture online. But someone went to the trouble of typing all these in for you. You probably don't want to write all those down every single time. But those are all of our possible outcomes. It is, if I roll 1, my second die could be a 1, 2, 3, 4, 5, or 6. If I roll a 2 on my first die, then I could have a 1, 2, 3, 4, 5, or 6. If you count them all up, you will have 36 possible outcomes. You do not want to have to write this every single time. So a more efficient way to get your possible outcomes. A more efficient way to get your possible outcomes, especially if I say, well, we're going to roll 3 die now. That's going to be 216 things you'd have to write down. I wouldn't want to do that. I don't want to make you do that. So instead of drawing them all out, I'm just going to say, well, possible outcomes are going to equal, well, if I roll 1 die, I have 6 possible outcomes. That is if I just do 1 die. my second die or my second roll would also have 6 possible outcomes. Call that my 2 die, I guess. Sounds weird. My second die. 2 die or not 2 die. All right. We're going to use the fundamental counting principle. We're going to say if I have 6 possibilities on the first die, 6 possibilities with the second die, then my total number of possibilities would be 6 times 6, which would be 36. Now if I asked for you to roll another die, you would just multiply that by 6, which would be 216. All right, so our total possible outcomes is 36. So we'll put that on the bottom of our fraction. Now, you can either look up there or you can just think in your head, what are all the possible combinations that equal 5 when you roll one die? I always start with 1. 1 plus 4 equals 5. Then I'd flip it and say, well, 4 plus 1 equals 5. Then I'd say 2 plus 3 equals 5. And finally, 3 plus 2 equals 5. There are 4 of them. And if you look at our sample space here, if you just circle the ones that are 5, 4 and 1, 3, 2, 2, 3, 1, 4, you would see that there are 4 ones that add up to 5. And that's just going to equal 1 over 9. But rather than having to draw those out, you want to kind of come up with those tricks. You want to figure out 6 times 6 equals 36. Those are our possible outcomes. And then you should be able to kind of picture in your head which numbers add up to that actual 36. All right, my next question says, find the probability that you will roll a 6 and then you will roll a 5. I want you to think about that. You're going to roll a 6 and then you're going to roll a 5. Who wants to venture a guess at what the probability is of me first rolling a 6 and then me rolling a 5? No one wants to venture a guess? Yeah. It is 1 out of not 30. Did you say 30? Out of 36. Yeah, 1 out of 36 because we have 36 possibilities. Yes, it will be 1 over 36 because there's only one option. I have to roll a 6 and then I have to roll a 5. That means there's only one outcome. Which means we have 1 over 36, where 36 is my possible. That was my 6 times 6, gave me that 36. Or you could have counted them up. And my answer is 1 out of 36. Do not overthink these. Just ask yourself, how many times does it happen? How many times can I roll a 6 and then a 5? It can happen once. If I said, what are the probability of you rolling a 6, a 5, and then a 3, it would be 1 over 216 because your possibilities would become 216 because you'd multiply this by 6. But your top number would still be 1. You'd have to roll a 6, a 5, and then I already forgot what number I said was the other one, but whatever I said, that would be your third number. All right, the next thing we're talking about is compound probability. Simple was just one event. Compound is going to be a couple events happening, 2 or more. And either going to be independent or they're going to be dependent. Let's talk about independent first. So it says that the outcome of the first event does not affect the outcome of the second event. The example was rolling a 6 and then rolling a 5. If I roll a 6 with a die, does that affect what my next roll is going to be in any way, shape, or form? No, it doesn't affect it at all. That's why it's independent. Here's a key thing I want you to point out right here, because this is what signifies it is a compound event. And that is that symbol there. That symbol is a mathematical symbol for and. So this statement is the probability of A and B happening equals the probability of A times the probability of B. Your key word for compound probability is and. And is important. It doesn't look like it is, but it is because tomorrow we're going to talk about or. There's a big difference between and and or in life, and there's a big difference between and or in math. So this is our and section. Tomorrow is our or section. Dependent. If independent is where they don't affect each other, dependent must be where they actually affect each other. So outcome of the first event does affect the outcome of the second. So my example was, without replacing the first card, choosing an ace, and then choosing a king from a deck of cards. So I have a pack of cards right here. Picture it in my hand. And I go, Ahmed, pick a card. And he...
Ace.
You got to grab it. There. What'd you get?
I got an ace.
You got an ace. He's not going to replace it. How many cards are now in my hand?
51.
There's 51. So if I now face Joe and I say, Joe, pick a card, he's only got 51 to pick from.
I picked all 51 of them.
He got all 51 of them. No, he would have got, what did I say he got? A king.
Oh.
But did Ahmed picking a card and holding on to it change the odds for Joe picking? Yes, that's what makes it dependent. It is dependent on what Ahmed picked because he kept it. That will affect the odds for Joe. Consider if we were doing both had to get an ace. And I do this and Ahmed picks an ace. Joe, there's only 3 aces left. His probability went way down. So that would be dependent because it's dependent on the other thing. Note again, we have that and symbol right between the A and the B. So this is the probability of A and B is going to equal the probability of A times the probability of B, taking into account how A affected it. So in this case, it would be, I would no longer have 52 cards. I would have 51 cards for Joe to pick from. And then we'll just go ahead. So now we got those straight. Let's see how they work into a problem. So it says find the probability that you will roll a 6 and then you will roll a 5. We already said that's independent. They don't affect each other. Whatever I roll first, who cares? I move on to the second one. So this is independent. If it's independent, you just got to find the probability of one and multiply it by the probability of the other. So in this case, my probability of rolling a 6, that's going to be 1 over 6. There's 1 6 out of our possible 1, 2, 3, 4, 5, 6. Our probability of getting a 5 rolling would also be 1 over 6. Now we're going to note that we said probability of 6 and probability of 5. That and tells me to multiply. And we're going to have 1 over 36. We already did this exact same problem, didn't we? Like 2 problems before. This is 2 different ways to do the same problem. But you should believe that it is true that it's 1 over 36 because we can do it with the picture. We could say there's 1 6 over 5 out of 36. Or we can treat it as 2 different events that I'm flipping a coin or rolling a die and then rolling a die. Our next one says a bag contains 3 marbles, 3 red marbles, 2 green marbles, 4 blue marbles, and 2 marbles are drawn randomly from the bag and not replaced. Your key word in this one is that not replaced. If I do not replace the marble, it's going to affect my second marble. So this will be dependent. It is dependent on the first one I grab. And it is terribly dependent. Now, once it's dependent, we just have to figure out what's the probability of the first thing happening and multiply it by the probability of the second thing happening. And we take into account that the first one we picked will affect that second probability. So let's read the question. The question says, find the probability of both your marbles are blue. So let's find the probability of me just picking 1 marble and it happens to be blue. That was a P that turned into a B. Probability of picking a blue. My probability of picking a blue. What is my probability of picking a blue? Joe?
Whoa, sorry. Wow.
That's okay.
2 nens. Wait, sorry, what? Never mind. Forgot about this. I should have done this.
That's okay. Yeah.
Is it 4 over 10?
It would be 4, not over 10.
9. Oh, 9.
It happened in every class. Every class it was 10. Because we have 9 marbles, and maybe we'll put that, our possible outcomes would be 9 marbles. I don't know what is about it, but everyone thought it was 10. I think it was just the quick. But you understand why it's 9, right?
Yeah.
Yeah. Because we have 4 blue over 9 total marbles. All right, now we're going to talk about that probability of getting that second blue. But remember, the first one does affect the second one. So Ahmed grabbed into the bag and grabbed a blue marble. How many blue marbles are still in that bag?
There's going to be 3.
There's going to be 3 left, so my top is going to be 3. How many total marbles are in that bag?
8.
8. So it's going to be 3 over 8. And we're going to multiply those together. So maybe I'll put a little note here. Maybe I'll put it in red. This is because I removed a blue. And this is because I removed any marble. It doesn't matter if it was a blue, red. I just removed a marble.
I was listening. I just had a dyslexic moment.
Okay. All right, that's going to equal 12 over 72, which is actually going to equal 1 over 6. Be careful. This top number doesn't always change. What if I would have said you're going to choose a red marble first? In that case, our first number would be 3 over 9. And then if I said choose a blue marble, this would be 4 over 8. All right, because I didn't take a blue marble out, I took a red marble out. So be very conscious about what color you're taking out and how it affects this second number. It won't always affect the top. It will most likely always affect the bottom, though, because you're always taking a marble out. Does that make sense, or did I make it more confusing? Or just blank stares? Okay, blank stares. Are you okay with the sun? Okay. I say that because people won't close it, and they're like, yeah, it's really bugging me. And I'm just like, well, close it. All right, a couple have just given birth to a baby boy. Girl.
Yes.
Whew, you'd think this wasn't my 4th time reading it. What is the probability that the next 2, that should be a TWO, 2 children will also be girls? Yes?
Would it be like 50-50? Because like having a girl doesn't determine what the next one's going to be.
Yes, each one's 50-50, right?
Yeah.
What you just said there is really key, though. You just said having a girl does not affect what's going to happen next, right?
Yeah.
So this is independent. It is independent. That's the key word you're looking for, is does it affect the other one? So it's independent. What was that?
Couple is singular. Yeah, it's a couple has.
Oh, anyway.
You're just correcting me.
Well, put it on yours. Okay, so a couple have just given birth to a baby girl. What I want to focus on is not the correct language of it. I want to focus on that statement there. They already had the baby girl, right?
Yeah.
Does that affect anything else?
No.
No. Are we going to factor that into our probability at all? No. Because it's independent, I don't care what already happened. I care about what's going to happen. If this was dependent, then I would care what happened. Let's say this is back to the marbles one. And I said there was 9 marbles in a bag, and I already pulled a red one out. That would affect all the rest of them because now I only have 8 marbles in that bag. So what already happened will affect. This is independent, so what already happened will not affect what's going to happen next. And what's going to happen next is they hopefully have 2 more girls. So let's talk about the probability of the next one being girl. Let's call that girl, 2. Ahmed already said it's 50-50, right? Mm-hmm. So that's a 1/2 probability that our next child or the next child is a girl. The third girl,
It's going to be 1/2 as well.
1/2 as well. And we are looking at an and statement because I have to have the second one and then the third one. We'll do some multiplication and come up with 1/4. So in fact, that first statement that I put up there, a couple have just given birth to a baby girl, doesn't matter, doesn't affect that at all. You really only care about what is the probability of their next 2 children will be also girls. All right. Your homework. The first one says, what is the probability of getting exactly 1 head when a pair of coins is tossed?
Getting
Exactly one head when a pair of coins is tossed. So rather than using any kind of weird compound kind of multiplication or anything, all I'm just going to picture in my head is the 4 different possible outcomes. And that is a head-head, head-tails, tails-heads, and tails-tails. There's only 4 possible outcomes. And that is our 2 times 2. Well, of those outcomes, how many of them have exactly one head in them? Well, I know it's not the head-head. I know it's not the tail-tail, so you're just left with 2 out of 4. Drawing all of your sample space can sometimes be a lot quicker than trying to go crazy with multiplications and stuff. All right, that applies to like number 7 because you're rolling a single die. It might make your life easy just to draw all the outcomes. Same thing with 8. You could just draw your outcomes. And then I'm looking at number 10D. 10D, D is in dog. That is a tough problem. That is a tough problem. It looks really easy, but you're going to get to it and it's going to be a tougher problem. My hint to you is calculate what you don't want rather than calculate what you want. That is my hint. It's a terrible hint, but it's still a hint.